Hello, I'm Professor Bill Chaplin from the University of Birmingham, and today I'm going to be giving you a brief overview of the NASA TESS mission, which was launched just over 2 years ago. I'm a stellar astronomer, and now is a particularly exciting time to be able to study stars, since our ability to do that is being driven by a new generation of satellites and telescopes that are providing us with data of unrivaled quality on unprecedented numbers of stars. Stars are the building blocks of the galaxy. They drive its chemical evolution. And so by studying large numbers of individual stars, populations of stars, that tells us something about the evolution of the galaxy, its past, and also as well its future. But of course, studying stars on an individual basis is vitally important for informing our knowledge of stellar evolution theory. And of course, then the influence that stars have on their local environments, the fact that they act as safe harbors for planets and provide the energy needed to be able to give conditions that might support life on the surfaces of those planets. It's really this mission that really has revolutionized observational astrophysics for studies of stars and searching for planets around those stars, the NASA Kepler mission. Kepler was launched in 2009 with its prime objective to search for small terrestrial Earth-like planets orbiting sun-like stars. But also as well, it provided the data that enabled us to be able to study the stars themselves. And we were very, very lucky to be involved with the Kepler mission right from the outset, as I'll go on to explain. Kepler's main goal was detecting planets via the so-called transit method. So this is the very simple, elegant idea that if you're observing a star around which a planet is orbiting, and you're also observing the plane of the orbit of the planet edge on, there will be times during the orbit when the planet will pass in front of the star, it will transit the star, and if you're measuring the brightness of the star, you'll see a characteristic dimming, as shown here, which is called a transit. Of course, if you observe long enough, you'll see that transit come round again and again and again as the planet completes successive orbits of the star. So here one is detecting planets indirectly by the impact that the light has on the planet from the star. And Kepler has been tremendously successful in discovering literally thousands of planets orbiting sun-like stars, which are in our local solar neighborhood and nearby parts of our galaxy. Now, because the planet is detected indirectly, in order to be able to say, for example, how large the planet is, also how massive the planet is as well, whether or not the planet might perhaps be orbiting in the habitable zone, the so-called Goldilocks zone, not too hot, not too cold, but just right around its host star. You need to know the properties of the host star in great detail. So you need to know its size, its mass, also how hot its surface is. That tells you how luminous the star is and how much energy it's therefore emitting. So the studies of planets go hand in hand with the studies of stars. Of course, studying stars, as I mentioned earlier, is of tremendous importance, of course, for informing our knowledge of the evolution of stars and populations of stars in the galaxy. But also as well, this goes hand in hand as well with informing our understanding of the planets that we're actually discovering. Now, the data that Kepler was recording, so measuring the brightness of stars, also enabled us to study the stars themselves by the small intrinsic variations in brightness that came about because of things happening on the surfaces of the stars. Be that, for example, small variations in the light levels due to regions of activity, like dark spots on the surface of the star, but also my particular area, changes in the brightness of the star resulting from sound waves or waves trapped inside the stars, giving rise to gentle oscillations. And this is the field of Astro seismology. So as the definition says here, and this really is in the Oxford English Dictionary, the study of the interior of stars by observation and analysis of oscillations at their surface. So stars make sound naturally in their interiors. The sound is trapped, even though a star doesn't have solid edges. it nevertheless acts as a cavity to trap the sound. You get standing waves set up then within the body of the star. And again, because the star is a big ball of gas, those compressions and rarefactions of those standing waves make the star oscillate. As the star breathes in, it gets hotter and brighter. And as it breathes out, it gets cooler and darker. So by measuring these periodic variations in brightness, we can actually learn about the internal properties of the star, because the variations in the light are telling us about the sound waves trapped inside, and the properties of those sound waves are affected by the properties of the material of the gas through which they're traveling. But also as well, not only can we build up a picture of what the inside of a star looks like, we can use the study of these oscillations to as well produce very precise and accurate measurements of the radii of these stars, also as well incredibly precise measurements of the mass, and also as well the ages of these stars. And those are the basic data that we need to be able to get a better understanding of the planets that we discover around those stars. So here's an example of the type of data we might get on a star. This is a planet hosting star called Kepler 66, and this is the spectrum of its oscillations. So stars don't just oscillate in one or two different modes or tones, they do so in many different overtones. So just in the same way that a musical instrument will resonate not just at one note, but in several overtones or harmonics, the star does the same. So when we observe the brightness variations of the star, we're not just seeing the result of one oscillation, we're seeing the composite effect of many oscillations. And if we look at do a frequency analysis of those brightness variations as a function of time, we can get something that looks like this, that's showing here on the vertical axis, if you like, the strength of the signal, and the horizontal axis is showing the signal strength at different frequencies. And you can see this characteristic cone-like pattern, just like the pattern we'd see from a musical instrument, showing all the natural intrinsic overtones of the star. And it's by measuring these overtones that we can build up this detailed picture of the interior of the star, and also measure with great detail its fundamental properties. So that's the field of astroseismology. Our involvement in Kepler in Birmingham was to lead work by a large international consortium called the Kepler Astroseismic Science Consortium that comprised about 500 scientists. And we were leading the large group of around about 150, 200 people that were studying sun-like stars, and also as well, a group as well that was characterizing the brightest planet hosting stars that were discovered, around which planets were discovered using astroseismology. Now, Kepler really, as I said, it's no understatement to say it really has revolutionized our ability to be able to study stars. But what Kepler did for the first 4 years of its mission was to study stars in a very tiny patch of the sky. It then went on to observe stars distributed around the ecliptic, but it wasn't observing the very, very brightest stars in the sky. So come the last decade, we were very excited to hear about and to get involved from very early on in this, a successor mission, the NASA TESS mission. So TESS is an acronym, the Transiting Exoplanet Survey Satellite. And we got involved from very early on in terms of actually setting up the TESS Astroseismic Science Consortium, and also again leading those parts of the consortium involving many scientists studying sun-like stars, and also as well the planet hosting stars. Now, what TESS was designed to do, which Kepler did not, was first of all to observe the very, very brightest stars in the sky, to as well look to, just like Kepler, look for brightness variations due to the presence of planets, but also as well to use those brightness variations to study the stars themselves. But also as well, unlike Kepler, which at any one time was only observing small patches of the sky, TESS was designed to observe a much larger fraction of the sky at any one time, as we'll go on to see, and also over the course of a 2-year mission to basically survey all of the brightest stars right across almost the entire night sky. Now Kepler as well, one of the difference was in terms of the size of the satellite. Kepler was about the size of a bus, and you can see here TESS is much, much smaller. Now TESS makes its observations through via the 4 cameras that you can see here. And you can see that the alignment of the cameras is such that they are stacked, so that at any one time, each of these cameras is observing a slightly different patch of the sky, and basically measuring the brightness of all of the objects, be they stars or maybe solar system objects, planets or maybe comets, that fall within the field of view of each of the cameras. So this image here shows how that works. So the little figure at the center of the screen here, that's showing a little graphic, tiny graphic of the TESS satellite itself. And then if we look at this patch of the sky here, each of the 4 cameras has a field of view that's essentially a little sort of square on the sky. And then at any one time, the cameras are oriented so that they each observe a patch that basically maps out a sector on the sky that looks like this. If you like, a little bit like a strip from half of a Terry's chocolate orange. And what happens is that the satellite will basically stare at that fixed field of view for around about a month. So you're observing continuously the brightness of any objects that fall within these fields of view of the cameras for about a month. Then what happens is that the satellite rotates round and observes the next strip of sky. And then after observing that strip for a month, it then rotates round and observes the next strip, and so on. So that over the course of about a year, you've basically mapped out one hemisphere. The satellite then flips over and observes the other hemisphere. So over the course of approximately 2 years, you've basically mapped the brightness of all the stars in the sky, pretty much the entire sky. The coverage isn't complete. TESS was designed deliberately not to observe stars in the ecliptic. And as you can see here implied by this image, there are a few small gaps, but nevertheless, you're observing pretty much all of the bright stuff right across the sky. So here's another image here representing again the observing strategy. So again, here you can see in this left-hand image here, how each of the 4 cameras is observing a small patch of sky, which combines to form a strip that's observed across any one month. And again, as you move on in the next month, you observe the next strip and so on. So that after 13 of these sectors, so each sector actually lasts about 27 days, you've mapped essentially most of an entire hemisphere. Now, the closer you get to the ecliptic poles, so this is the ecliptic here, okay, and the orientation is such that you've got the ecliptic north pole pointing upwards, the ecliptic south pole pointing downwards. You can see here that there are going to be regions as you get closer to the poles, which are observed possibly in 2 or even more of these different observing sectors. The image on the right-hand side here shows the coverage of that. So you can see that the way things are oriented, stars actually close to the poles essentially get observed for the entire year. So it's actually 351 days. And then stars that are close to the ecliptic plane here. So for example, stars that are observed here by this camera, the camera that's observing closest to the ecliptic, are going to be ones that only ever fall within the field of view of that camera at that time, and they only ever get 27 days of data. The image on the right-hand side here as well shows the regions that were not covered during the so-called nominal mission. So these little patches here, and also as well the region close to the ecliptic. That was a deliberate choice because Kepler actually observed many regions of the ecliptic during its nominal mission. So TESS's nominal mission, designed to last 2 years, essentially doing a 1-year survey of each celestial hemisphere. Things actually started off like this. So it actually did the southern celestial hemisphere during its first year of operations, and then flipped over to do the northern celestial hemisphere. And those observations were completed, actually, this nominal mission was completed earlier this year. So that was the observing strategy, again, basically providing these exquisite measurements of the brightness of objects falling within the field of view. The primary goal being the observation of the brightest stars in the sky, but again, just picking up any other objects that would fall within the field of view, be they solar system objects or distant galaxies as well. So we wind back time then to just over 2 years ago, well, a bit more than 2 years ago now, to April 2018, and the launch of TESS at Cape Canaveral. I was very lucky to be one of the people, because of my involvement in the preparations for the mission, to be invited to the launch, which was fantastic. Still definitely my favorite ever work trip. And here's an image here of the top of the Falcon 9 rocket on which TESS was launched. So you can see here the so-called fairing. So this is the part of the rocket that protects the satellite during the phase of the launch when it's going through the Earth's lower atmosphere. Just again to reiterate size scale here, remember we saw how TESS isn't a very, very big satellite, and that sort of reinforces the point. You had this tiny, tiny satellite about the size of a fridge freezer right at the bottom of the fairings there. So that was the mission all set up, ready to go at the top of its Falcon 9 rocket at Cape Canaveral. Here are a few gratuitous pictures of me at Cape Canaveral at the site where we were at the, in inverted commas, a VIP site that we were lucky enough to be at for the launch. So this overlooked, you see the top image there, this actually looked across the water at one of the lakes, or I guess the lagoons at Cape Canaveral, looking onto the launch site that was just a few miles away. And initially, actually, we were there for several days. The first launch attempt, which happened a couple of days prior to the final successful launch that we're seeing here, the first attempt was actually scrubbed just as we were actually on our way on the buses out to the site to actually watch the launch itself. But we were lucky enough that we booked our flight such that we were able to hang on. We just had a insurance of about a day, so we were quite lucky that we were there actually for the actual launch that happened on April the 18th. And here's a nice image of that. This, of course, is not a picture taken by me. Here's a picture taken by me, okay? So this gives you an idea of the launch. So I'm not the world's greatest photographer. Here's a couple more attempts made by me to show the launch. So it's fantastic actually being there. Obviously quite nervous because we've been obviously involved in a lot of the preparations for the mission in terms of setting up, helping to set up this consortium, planning all the analysis we were going to do with the data. So a real relief that the launch went off without a hitch. Also a fantastic experience to see a real launch in the flesh. So I told many people who've asked about what it was like, the most striking thing was just how bright the plume of the rocket was. Also the noise as well, but the brightness of the plume of the rocket was the most striking thing. So that put TESS into orbit. It took a few weeks before it actually got into its science orbit. But once there, it was able to take its first light image, and this is the image here. So this really gives an impression here of the exquisite detail and the rich information content in these images. So if we look at the center of this slide here, so each of these squares here, the 1, 2, 3, and 4, is showing a snapshot taken by each of the 4 cameras at this particular time. And then you can see in a bit more detail then at the edges the rich content of these images here, showing a whole variety of different types of objects, of course dominated by the presence of stars. So it's from these basic images that we're able to extract light curves of the stars from analyzing the brightness variation over the course of the month or even longer that stars are observed, capturing variations in the brightness of the light of these individual objects over time that produces a light curve. And it's from those intrinsic variations that we can learn about the intrinsic properties, characteristics, and parameters of the objects that we're actually observing. So one of the first things that we had to do actually prior to the launch was actually deciding which targets were actually going to be observed at the higher cadence that TESS had. So this is observing the brightness of stars on a 2-minute cadence. And we need that rapid cadence to be able to follow the intrinsic brightness variations that result from oscillations in sun-like stars. And they have prominent periods of the order of several minutes. So you need to be able to capture those variations. Hence, we need to observe them in this mode of operation where the brightness is recorded every 2 minutes. So one of the big jobs that we had prior to launch was actually deciding which targets would be observed for astroseismology. And one of the things here in Birmingham that we did was actually leading the work on deciding which of the targets, which of the sun-like or solar type targets would be observed. And that was selecting out around about 20,000 stars that would go then on the target list and be observed by TESS during the nominal mission. So here's an example of some of the sort of data that we got in some of the, I've picked out just a couple of examples here from early publications that we produced. Here's the oscillation spectrum of a naked eye star called New Indy. So again, one of the things that TESS gave us that Kepler didn't was the ability to observe the brightness variations of the very brightest stars in the sky, stars we can observe with the naked eye. So here's the oscillation spectrum of this star. You can see here from the title of the slide, this is talking about age dating a collision or a merger that the Milky Way underwent using data on just this one individual star. So how does that work? So from this oscillation spectrum, and also from other information that we know about the star, we knew already from the other observations of this star that it was a very old star. It's been around in the galaxy for a very long time. And from these data, from measuring the frequencies of all the different components of oscillation we can see here, we were able to place very, very tight constraints on the age of this star. Also, as well, from other information on this star as well, we could pin down the fact that this was a star which was born within our galaxy. And it was not a star that ended up being in our galaxy because of the collision of another galaxy. And there have been several collisions the Milky Way has undergone throughout its history. One that has garnered particular interest over the last sort of couple of years has been the collision of a galaxy called Gaia Enceladus. The fact that this large galaxy, which had a mass that was about a quarter of the mass of the Milky Way, the fact this galaxy had collided with the Milky Way and details of that collision really came to light as a result of the wealth of data we got from the European Space Agency Gaia mission. So very early in its history, the Milky Way underwent this collision. And as a result of this collision and other collisions have helped to shape the evolution and also as well the content of stars within the Milky Way, leading to the galaxy that we actually see now. But one thing that we know from looking at this particular star, New Indy, we know it was born within the galaxy, so it didn't come in with Gaia Enceladus, but we know that its motion within the galaxy was actually affected by this impact. And as a result of that, it enabled us to place constraints on when this merger happened. So that's a really nice example of showing how data on just one very bright star can tell you something about the overall history of the galaxy. But one of the other things, of course, we've been doing with TESS is using astroseismology of planet hosting stars to parameterize and constrain the properties of the host star, and hence, therefore, to place constraints on the planets that have been discovered. So this was actually the first system with TESS, where TESS had discovered a planet, and the star also was bright enough to enable us to do the astroseismology. So on the left-hand side, we've got the overtone spectrum of the star. We used that then to measure the properties of the star in great detail. On the right-hand side, we've got the transit curve produced by the dimming of the planet as it orbits the star. That's the TESS data. With this star as well, with ground-based telescopes, we were able to as well observe or detect the planet, the presence of the planet as well, from it pulling or tugging on the star, giving rise to variations in the velocity of the star. And that gives rise to this radial velocity light curve or Doppler wobble signal on the bottom right-hand side. And by combining all these data, that enabled us to actually provide a measurement of the absolute size of the planet from the transit data, combined with the absolute size of the star. And also we could as well measure the absolute mass of the planet from the Doppler wobble data, combined with the mass of the planet inferred from the analysis of the star that used the Astro seismology. And we're now starting to do this as well on more systems. One other thing that we were involved in as well last year was actually preparing the case to NASA to actually get the mission extended. So one of the things I helped to do was to actually coordinate the input that the Astro seismology community provided to the so-called NASA Senior Review process. The mission was extended. It's been a great success so far. And as of now, it's now into its extended mission phase. TESS will have enough fuel on board to, in principle, be able to continue its mission for maybe a decade or more. So there are real prospects here for TESS to be able to continue on taking its data, fingers crossed, for many, many more years to come. And there will be exciting opportunities in the future to actually come up with new modes of observing and have TESS focus on different parts of the sky for detecting and collecting different types of data. So the future is very, very bright with TESS. I think TESS is going to be carrying on collecting data, possibly all the way through to the end of my research career. And with that, I will end. I hope I've given you a bit of a feel for the TESS mission and all of the exciting results that it's already produced and it will go on producing over the coming few years.